Ian, please.
Okay. First of all, thank you for inviting me to speak at the seminar. I'm going to speak about the hidden structure in April's proof, where he showed that the Riemann zeta value of 3 is irrational. Now, I first learned about this proof about a year ago when I first started to work with the Ramanujan machine group at Technion. And to tell you the truth, up until now, I'm not really sure what happens in his proof. But in the Ramanujan machine group, what they did before I came and when I came also, is that we try to study polynomial continued fractions using all sorts of computer algorithms. And one of the things that we managed to find during this investigation is this nice mathematical structure that we think gives some motivation and some explanation to what Apri did in his proof. So this is more or less what I want to talk about today. Okay, so let's start with something really simple. I want to ask, how do we prove irrationality for some numbers? And let's start with the most simple example, the square root of 2. This is something that probably all of us learn on the first semester, and maybe the lucky of us even before that. So square root of 2 is an algebraic number, so we want to use its algebraic definition. And the standard proof goes as follows. You say that if square root of 2 by negation was some rational number p over q, then you switch sides and you get that 2 times q squared equals p squared. And whenever you have a solution with integers to this equation, then it is easy to check that both p and q are divisible by 2. So this p over q rational is actually, it is not a reduced rational, right? 2 divides both p and q. And of course, this is a contradiction because whenever you have some rational number, you have also a reduced form rational number. So this is a very, very simple example of proving that a number is irrational. And basically today we know that all the algebraic integers, which are not themselves integers, are irrational. So this is really the first step. And if all the numbers that we have are algebraic, then we are done here. But fortunately, we have numbers which are not algebraic. And the prime example is e, the exponent. And here it is not algebraic, so we need to use some sort of analytic definition. And here came Euler in 1737 and used the well-known theorem that a number is irrational if and only if it has an infinite continued fraction expansion. And if you want to prove irrationality for this for e, then you need to find out if it has an infinite continued fraction. But the problem is that usually when you want to find the continued fraction of a number, you need to do the Euclidean division algorithm. And now you need to do an infinite Euclidean division algorithm, which is, of course, really hard to do. So here Euler had a nice trick. And he noticed that if you write a continued fraction of e, then you have this nice pattern of 1 to 1, 1 for 1, 161, 181, and it carries on, it continues on indefinitely. And in particular, if it continues on until infinity, then e has an infinite continued fraction expansion. So this trick of looking at a continued fraction, notice that you have a nice pattern inside it, and therefore it is irrational, is this nice proof that Euler had. Okay, at least for me, the problem with this proof is that many people don't know what are continued fractions, and even those of us that do know, a lot of us don't know what is the continued fraction of e. So the question is there another proof which is more elementary? And here really came Fourier in 1815, and he told Euler that, you know, you don't need to go all the way to continued fractions. It is good enough to find good enough rational approximations. So what do I mean by that? Take the standard rational approximation of e, right? I take the sum of 1 over k factorial from 1 to n. And let's look on the error to this rational approximation. So assume by negation that e is a rational number.
If you're trying to make it go to 0, you need to start from 0 to n.
Yeah, you are right. The proof is still the same, but yeah, it should be 0 here. I will fix it for the next talk. Anyway, if you look at the error, if you assume by negation that e is a rational number, it is m divided by n, then the error itself is going to be a rational number. And moreover, if we stop here at n, then this rational number, we can write it as with denominator n factorial. Right? So this error, in a sense, is discrete. Once I fix the denominator to be n factorial, then the numerator must be an integer. So this is on the one hand. On the other hand, we know exactly what the error should be if I started at 0 and not at 1. It is going to be n plus 1 until infinity, the sum of 1 over k factorial. And this is, of course, a positive number. And we can write it, we can take out the 1 over n factorial outside and get some infinite sum. And it's not hard to show that this infinite sum can be bounded from above by this geometric sequence. And it's not hard to show that this geometric sequence is bounded from above by 1. So all in all, what we managed to show is that you have very good rational approximation for E, in the sense that the error is very, very small, right? It is between 0 and 1 over n factorial. And under our assumptions that E is going to be a rational number, this error is also discrete. So it is an integer divided by n factorial. So this integer should be strictly between 0 and 1. And this is a contradiction. So this is, in a sense, it is very elementary, right? You can show it to first semester students. And we managed to show that E is irrational just by using that it has very good rational approximation. Okay, so to summarize these two methods, we had Euler and we had Fourier. And Euler said you should go all the way to continued fractions, which in a sense give us the best rational approximations.
Yeah, I should mention that the sum of the reciprocals of the factorials, by the standards of continued fractions, it is not a very good rational approximation. The error is not shrinking quadratically in the denominator, not at all.
Yeah, but it was good enough to show irrationality. Exactly. So this is what I mean in good enough. And this is exactly the point that Euler said you should go to continued fractions because in a sense they are the best rational approximations. But usually continued fractions are hard to find, right? You need to do the Euclidean division algorithm. So you need to look for some nice patterns. And Fourier said that you don't need to go all the way to continued fractions. It is good enough if you find what we say good enough rational approximations. Okay, so these are the two analytic methods of showing irrationality. Okay, so this was E. Let's see another example. Let's see pi. And if we start with Euler's methods and we write pi as a continued fraction and we want to find some nice pattern inside pi, and we see that we have here the 1, 1, 1, and I hope that you see my mouse also. Mm-hmm. And you might think that, okay, maybe I can find some nice pattern, maybe the ones repeat up to infinity, but actually this is not the case. And if you write a little bit more, then it stops. But then again, you find this 2, 2, 2, 2 suddenly, and maybe this is a nice pattern, but actually this also stops immediately after these 4 2s. And actually, I think that there isn't any known pattern inside pi that we can actually use. So we can't use Euler method directly. So now we still want to prove that pi is irrational, because it is irrational. And here came Lambert in 1761, and in a sense combined both of Euler and Fourier's method, even though it was before Fourier. And he showed the following. He first showed that tangents of x can be written using this nice expression. So this is not exactly continued fractions because we don't have 1 in the numerators, but it is very close to continued fraction, right? We have this similar structure. But moreover, it has a very nice pattern that we can exploit, right? We have all of the denominators except the first one are x squared, and all the numerators are odd integers. So this is a very nice expression that we can try to use and prove some stuff. So this is the first claim. And then Lambert shows that if you give me a non-zero rational number, then using this expression, you can show that tangents of x is irrational. Okay, so this is his second claim. And now come the easy part. If you assume by negation that pi is rational, then pi over 4 is rational, and then tangents of pi over 4 should be irrational, but tangents of pi over 4 is exactly 1, right? This is just tangents of 45 degrees. And 1 is, of course, a very rational number, so we get a contradiction. So now we get back that pi must be an irrational number. So again, the trick here is that we look at something which looks like a continued fraction, but it is not exactly a continued fraction. And on the other hand, we have very nice patterns that we can use, right? We have the x squared here, and we have these odd numbers here. Okay, so these were E and pi. Let's look on one more example. Let's look on the Riemann zeta values. So zeta of 2, by definition, is the sum from 1 to infinity of 1 over k squared. And we know how to compute this. This is actually pi squared divided by 6. And we already saw that pi is, of course, irrational, but it doesn't mean that pi squared over 6 is irrational, just because we know that pi is irrational. However, by today, we also know that pi is actually transcendental, right? It is not a root of any polynomial over the integers. And therefore, pi squared divided by 6 is also transcendental, and therefore it is not rational. So this is another nice way of showing that a number is not rational. And the same is true for any even valuation of zeta. Actually, there is a result showing that zeta of 2d divided by pi to the 2d is a rational number. And the same argument will show that zeta of 2d is transcendental and therefore irrational. But this proof fails for zeta of 3, or at least it is not known for zeta of 3. And now we have something interesting. We want to show that zeta of 3 is actually an irrational number. So here came Apéry in 1978 and showed that actually zeta of 3 is irrational. And the problem, as I said before, is that his proof is really complicated. It is actually really elementary, but following that we can actually... Sorry? Okay, so the proof is elementary, but following it is really hard. And actually, I think that every time that I saw someone mention Apéry's proof, they also mention another paper by van der Putten, whose sole purpose of this paper is to reprove Apéry and to try to understand what happens. So let me take a look on this paper. So this paper is called A Proof That Euler Missed, in case you want to look it up. So it is by van der Putten. And the first paragraph of this paper goes as follows. The board of program changes informed us as R. Apéry is going to speak about the rationalities of zeta 3. And though there had been earlier rumors of his claiming a proof, skepticism was general, and the lecture tended to strengthen this view to rank disbelief. And I'm not sure about you, I think that this is a great way to start a first paragraph of your paper. And then he continues, those who listen casually or who are afflicted with being non-francophone appear to hear only a sequence of unlikely assertions. So this is what I read when I first started to try to understand Apéry. And I will not going to give you those unlikely assertions because, again, I'm not fully understand them, but I will try to give what I think were the ideas behind these assertions. So these are the steps. The first thing is that you want to find good rational approximations, and they're going to imply rationality. The second step is that you should use recurrences to find these approximations. And the reason is that we understand recurrences quite well. For example, you can use this structure to, for example, bound the error rate from above. The fourth step is that you might get a good rational approximation, but it will usually not be good enough. So you need to find some way to improve this approximation. And finally, as with every proof, there is some secret ingredient. And as I said, the problem with Apéry's secret ingredient, it was really secret and it was really hard to understand. And it's not just I'm saying it, it's more or less van der Putten said it. And this is another paragraph from the paper. So section 5, it seems that Apéry has shown that zeta 3 is irrational. We were quite unable to prove that the sequence AN, whatever it is defined above, did satisfy the recurrence. And Apéry rather tartly pointed out to me in Helsinki that he regarded this more a compliment than a criticism of his method. But empirically or numerically, the evidence in favor was utterly compelling. Right? So even van der Putten, who tried to understand it, could not actually reprove it, but at least he ran some computer programs. And remember, this was in the 1970s. Right? This is quite old computer, and he managed to show that it should be correct. Okay, so what I will try to do is more or less go over this 5-step and try to convince you that this is a good way of proving irrationality, and along the way explain what are the objects that we worked with, the polynomial continued fractions, and how we got to the what we call conservative matrix field, which is the structure that we think stands behind a Paris proof. Okay, so let's start with what are good rational approximations. So take your favorite alpha, and let's say that we want to approximate it by a rational with denominator q. So of course it is very easy to see that you can always approximate it such that the error is at most 1 over q. Right? This is very easy because it is inside a segment of length 1 over q. And of course 1 over q is not enough in many cases. And here we have Dirichlet's theorem, which is a very interesting and very simple theorem, which shows that if you let me choose the denominator in a smart way, I can actually make sure that the error is at most 1 over q squared. Right? So these what are a very good rational approximation. So this is a very basic and very interesting result. And now I have a question for you. If I take alpha to be a rational number, is Dirichlet's theorem obvious? Can we always find very good rational approximation for a rational number? So, of course, the answer is yes. It is very easy to find very good rational approximation for alpha. Just take, if alpha is a divided by b, so just take an divided by bn. So the error is exactly 0. And this is, of course, smaller than 1 over bn squared. Right? So this is really obvious. But of course, this is a bit of cheating, right? Because I kept approximating alpha by itself. So this is not a real approximation. So let's say that I don't allow you to do it. And let's say that I ask you to find good rational approximation, but they are in a reduced form. So is it still obvious that you can find very good rational approximation for a rational number? So I claim that this is no longer obvious, and also this is no longer true. And let me show you why. Let's say that you have your rational number a over b, and you want to approximate it by p over q. So you look at the error. The error itself is going to be a rational number, which is not 0. So the numerator is at least 1. So everything is at least 1 over b times 1 over q. Now 1 over b is constant. Right, the b comes from the alpha which I have at the beginning. So we now see that the error is at least some constant divided by q. So Dirichlet gives us at most 1 over q squared, but now we see that it is at least more or less 1 over q. So now we have this nice gap, and to summarize, if we have an irrational number, then we can always find very good rational approximation. Right? The error is at most 1 over q squared. And if alpha is rational, then the error is at least some constant divided by q, as long as the approximation is not alpha itself. Right? So we have this gap between rationals and irrationals that one gives us at most 1 over q squared, and one gives us at least 1 over q. And let me just multiply by the denominator the two sides. Then a number is irrational if the product, if we can find such approximation where the product is at most 1 over q, and it is rational if the product is always at least some constant which is far from 0. So this gives us a nice irrationality test. You take your alpha, and you need to find some good rational approximations. And if the denominator times the error rate goes to 0, then your alpha is a rational number. So then the alpha is an irrational number. Right? So to show irrationality, just find good rational approximation in this sense. Okay, so I don't need the good in the sense of Dirichlet. I just need this convergence to 0. Okay, so this is our rationality testing. Let's see an example. And I will work with zeta 3 because this is the main player in our game. So let's take the standard rational approximation. So the sum from 1 to n of 1 over k cubed. And if I want to apply the rational irrationality testing, then I need the error rates, and I need the denominators. So the error rate is just the tail of the sum. So you go from n plus 1 to infinity of 1 over k cubed, which is more or less 1 over n squared. And to compute the denominators, we have a sum of many rational numbers. So for example, we can take the product of the denominators there, which is just n factorial cube. Now, if you take the denominators and you multiply by the error rate, it of course goes to infinity. So in this sense, this is a very, very bad rational approximation. Right? It doesn't even, it's not finite, and certainly it doesn't go to 0.
Yeah, the denominators, you're assuming quite a bit here. That is to say, you're assuming you've made the denominators as sort of bad, rather than you're not going to get n factorial if you take the least common multiple of the numbers from 1 to n.
Yeah, but please don't give spoilers. Yeah,
right.
exactly.
This
is the next step. Yeah.
Okay.
Yeah, so if I just do if I didn't know that I can take the least common multiple, I will just take the product. But if I do know that I can take the least common multiple, then this is exactly what I'm going to do to improve the approximation. And I can take the least common multiple of 1 until n, and you need to take the cube. And the least common multiple of 1 till n, it is more or less like e to the n. And of course, if I still multiply by 1 over n squared, so if I still multiply by the error, it still goes to infinity. But it goes to infinity much slower than what I had before. So this sort of argument that you start with the straightforward multiplication, then you manage to find that you can actually use the LCM, and you drop from a factorial to exponential. It's something that happens many times when you do this sort of computation, and we call it factorial reduction. Okay, so this is a really big improvement, but it is still not good enough. So at this point, we can try to find better improvements. And one way of doing it is just adding 1 over 2n squared to the approximation. And the reason that I just chose this 1 over 2n squared is that if you look at the error rate, this is going to jump from 1 over n squared to 1 over n cubed. Right? I improve the error rate. If I look at the denominators, with the LCM, then it doesn't change too much. Right? If I don't multiply everything and I just take the LCM, it doesn't change too much. So I still have the e to the 3n, and I still, if I multiply it by 1 divided by n cubed, it still goes to infinity, but it goes to infinity slower. So this is a nice step, and we can try to think that maybe we can do it again, and right, going from 1 over n cubed to 1 over n to the power of 4, 1 over n to the power of 5, power of 10, power of 100. And if I can do it again and again and again infinitely many times, maybe somewhere in the limit I will manage to show that the product goes to 0. So this is what I want to try to do. And the way of doing it is, instead of looking at the approximations as an infinite sum, is to think about them as recurrences. So this is really the next step. And let's try to build some recurrences instead of the infinite sums. So again, I take the zeta 3 and I take the standard approximation, and I will just write the numerators and denominators with the product, so the simple way of doing it. And before I go to 3-term recurrences, let's look at 2-term recurrence. And here, considering Qn as the n factorial cube, it is very easy to find 2-term recurrence. And Qn plus 1 is just n plus 1 cube times Qn. Right? This is why it is easier to work with the n factorial. The problem is, of course, that if I try the same recurrence for Pn, it doesn't work. But here there is a nice question which asks, how far is it from working? Right? If I look at the difference, how far it is from being 0. So it's not hard to just write down what we have. So for example, in Pn plus 1, we have this n plus 1 factorial, which goes out. In Pn, we have n factorial, but we also have this n plus 1. So we also have n plus 1 factorial cube. And you can check that the rest is just these two sums. And in these two sums, almost everything cancels out. And eventually, you just get n factorial cube. But n factorial cube was just the Qn that we started with. It is just the denominator. And we already know that this denominator has a 2-term recurrence. So in a sense, the Pn satisfy a two-term of a two-term recurrence, or in other words, they satisfy a three-term recurrence. Right? I have here Pn plus 1, and I have here Pn, and again Pn and Pn minus 1. So the Pn satisfy a three-term recurrence, but also the Qn satisfy the same three-term recurrence, because if I put Qn instead of the Pn, then this is 0, and this is 0. So we have 0 equals 0. So once we move to this three-term recurrence, suddenly we have that both the numerator and the denominator satisfy the same three-term recurrence, and this is this recurrence. Okay, so whenever we have recurrence, usually it is a good thing to do to move to a linear algebra and write it using matrices. And this is a really standard thing, and I guess all of you are familiar with this sort of matrices, because if instead of minus n to the 6 I will have here 1, then this is exactly the matrices that appear if you write standard continued fractions, right? If I have 1 in the numerators. So it is very helpful if you move to these matrix notations. And by the way, all the conversions that I did so far from infinite sums to this three-term recurrence, this is nothing new. This is actually something that Euler found out. It's called Euler conversion, or Euler continued fraction formula. Okay, so now that we have this three-term recurrence, then if you give me the initial conditions, you give me the P0 and P1, or Q0 and Q1, and you multiply by M1 until Mn minus 1, then you get the new Pn and new Qn. Right? You can get the numerators and denominators. And moreover, I want to look at the Pn divided by Qn, which is just the Möbius action of this matrix on 0. Right? This is just, you write it down and you see that this is just Pn divided by Qn. So we can see the rational approximation using this product of Mn and the Möbius action. Okay, so now we have this matrix, which is not, again, exactly polynomial.
Perhaps a very small correction.
Yeah.
If you apply the matrix to a vector, then you're going to get a vector. So what you're taking is the ratio between the components of the vector.
Yeah, so this is what I mean by the Möbius action.
Yeah, but it's not actually Pn over Qn. It's the vector Pn and then Qn. It's a pair of numbers rather than a single number.
No, I think about this as a Möbius action acting on the number 0, not the vector 0.
Okay.
Right? So the Möbius action acts on complex numbers, and when you act it on 0, you get Pn divided by Qn. But yeah, you're right. This is basically thinking about acting on the vector 0, 1, and you get Pn Qn, and then you take the division, which is just the Möbius action. Yeah, so you can think about it as vectors or as numbers. This is the same. Okay, in any case, we now have this nice polynomial matrix, which is very similar to continued fraction. It is not continued because we don't have here ones, but we get in return that this is a polynomial and this is a polynomial. So this leads us to what we call polynomial continued fraction, which for me is just a matrix which looks like that, right? It has 0 and 1 and 2 polynomials. And if I take the product of these matrices and apply it to 0, and I add here t, you should think about it as some sort of initial conditions, and I get this rational number. Or you can write it as something similar to the continued fraction. So here we have the ai's, and instead of 1, we have bi's. And now this is the polynomial continued fraction, and you can ask all sorts of questions about it. For example, does it converge? Because it is not automatic like with continued fractions. And if it converges, what can you say about the limit? And in particular, is the limit irrational? So let's see a few examples. Up until now, we talked about the zeta-3 case, right? And this is a very nice polynomial continued fraction, and it gives you zeta-3 up to a Möbius action. There is also a simpler polynomial continued fraction for E, and a simple polynomial continued fractions for pi. And remember, the continued fraction for pi was really, really complicated. The polynomial continued fraction is very simple. So there are many nice constants that you can find very nice polynomial continued fractions. And moreover, even if you just fix your constant, there are many polynomial continued fractions for the same constant. For example, here are a few which are related to E. All of these were found using the Ramanujan machine. And you can see that some of them are more similar. For example, these two are really similar. The Bn is the same. The An is just shift by 1. These two are similar. Again, the Bn are the same and the An is shift by 1. And this is really different than the rest of it. So we have all sorts of polynomial continued functions for E, and actually there are many, many more. And at this point, you should think about this many polynomial continued fractions of E as what we talked about before. Maybe one of them is the standard continued fraction for E, or the standard approximation for E. And when you move between the different polynomial continued fractions, in a sense, you improve your convergence. You get better and better rational approximation. So this should be the intuition when you see this many polynomial continued fractions. And this is the next step. But before that, I want to give the ways that
before you go, can I ask you a question?
Yeah.
What kind of numbers are representable by this type of continuous fractions? Is it a measure 1, measure 0, or what?
Yeah, okay. So if you assume that, first of all, everything that you can write with a nice infinite sum, like I did before with zeta 3, like you do with E, like you do with pi square is zeta of 2. Then,
by that you mean an infinite sum of rational numbers?
Yeah. So for example, you should think about infinite sum of some rational function, like 1 over n squared, which gives zeta of 2, or 1 over n factorial, which gives you E. So
you're looking at a countable collection of recursions, a countable collection of
yeah.
So if the question was what's the measure, because it's countable, it's measure 0.
0, yeah. Okay, that makes it clear. Thanks.
Okay, so
thanks.
The type of numbers that you should think about that we get are, if you have nice infinite sums, then usually you can translate it to a polynomial continued fraction. And if you just want to count them and you assume that both the polynomials are over this, then yes, it is countable. But of course, you can take something other than Z and work over Z because it is very simple.
Well, you're working over Z because you want to get proofs of irrationality. For that, you need to be able to work with the, what the size of the denominators and the numerators is. So you're not going to be able to do this over, arbitrary fields. You'll need, either the integers or some nice number field.
Yeah. So this is a bit of a spoiler for the end of the talk, but you want to work over some integer field, because if you show that something is not rational over an integer field, then of course it is not rational over integer extensions, and it's not rational over the integers themselves. Yeah. Okay, so now just in a visual point of view, we usually think about the polynomial matrices, the polynomial continued fractions, as a multiplication of many matrices, one over after the other. So you should think about it as starting from the identity, and then multiply by the first matrix, and then the second matrix, and then the third, and the fourth, and the fifth. And along the way, you get the numerators and denominators. So we should think about polynomial continued fractions as just an infinite array of matrix multiplication. So now that we have this visual way of viewing it, the approximations that we found so far for zeta of 3 is just one line. And what the people in the Ramanujan machine group did, this was before even before I came, they found many polynomial continued fractions which look similar to this one. And in a sense, this is just the first line. So they found all this family of polynomial continued fractions. And you can see that the Bn is always the same. It is minus n to the 6, like here. And the An is like we had before, just we had this extra term. So when m is 1 or 0, this is exactly here. And if you compute the limit of this polynomial continued fraction, you get something which is very close to zeta of 3. You just have the sum, but start with m instead of 1.
So the irrationality of any one of these is equivalent to the irrationality of zeta of 3.
Yeah, exactly. So they differ in some rational number. So now we have an infinite family of polynomial continued fraction, and we can think about it as infinitely horizontal lines. But they found something actually stronger. There is a second polynomial matrix. This is actually a polynomial because m minus n divides m to the cube minus n to the cube. And if you put it in the y direction, then this diagram is commutative. Right? If you first go to the right and then up, or if you first go up and then right, you compute the same matrix. And now suddenly you have many rational approximation, right? Every point is this lattice. You can just take the multiplication up until there and compute whatever rational numbers that you get, and you get some rational approximation. And what we managed to show that if you go along the diagonal, so again, you should think that the first line is the worst approximation, the second line is a better one, and the third line is a better one, and again and again and again. And in a sense, if you go along the diagonal, you get the maybe not the best, but a very, very good rational approximation. So eventually we managed to use it to show that zeta 3 is irrational, and the numbers that we got along the diagonal are more or less the numbers that Apéry got. So this is why we believe that, in a sense, this structure stands behind Apéry's result. Okay, so let's give a name for this new structure. We call it the conservative matrix field. And the definition is you just give me two polynomial matrices. Of course, it can be much higher dimension, but start with 2 for simplicity. And they need to satisfy this conservative condition. So the conservative condition is exactly take this square from before, and if you go right and up, and if you go up and right, and you do the multiplication of the matrices, you get exactly the same matrix. So this is a commutative diagram, or if you are into homological algebra, this is a one cocycle in the right set. So now we have this new definition, and of course, whenever you have a new definition, you should make sure that it has nice examples, and it does. So the examples that we saw before for Z3 is a conservative matrix field. By the way, we call it a conservative matrix field because it came from a conservative vector field, right? This is the intuition that most people have, at least most people who are not for mathematics and don't know what are one cocycles. So the Z3 that I showed you before is a conservative matrix field. We also have a matrix field for E. And again, you should think about it as we start with the bottom line, that it is a standard approximation for E, and then we build the matrix field above it. And we also have a conservative matrix field for pi, and I think for kata number, and for zeta 2, and all sorts of constants. So we already have nice example for this new object. And you should not try to understand the polynomials here. It is not really easy to understand, but there are some nice patterns that you should notice. First of all, if you look at the bottom left corners, then you just get ones. If you look at the top left corner of the x direction, you get 0. So all the x directions are polynomial continued matrices. And if you look at the top right corner of each pair, then they are the same, right? Minus n to the 6, minus n to the 6, and n. So there is some pattern here that maybe there is some constructions that it gives you many other examples. And indeed, there is a construction, and we managed to find it. And it goes as follows. You need to give me two polynomials which satisfy a very nice condition. The first one is a linear condition. So you evaluate this polynomial in 4 points, and you can check that these are exactly the 4 points of a square, but shifted by -1 somewhere. And the left and the right side should be the same. And there is a quadratic condition. Now you look on f times f bar, so it is a polynomial. And again, you evaluate it at 4 points of a very large square. But also this condition is equivalent of saying, take the polynomial ff bar, and this polynomial should not have any mixed monomials. So x to the n, y to the m, where both n and m are positive. So if you give me two such polynomials which satisfy these two nice conditions, and you call this part a of xy and this part b of x, which depends only on x, and you write these matrices, then this is going to be a conservative matrix field. So this is a very nice construction, and all the examples that I've shown you before are of this type of construction. So already we have I think at least, a nice mathematical object. We have a nice construction for such matrix field, and we have several examples, but actually it has many more interesting properties. And let's talk about some of them. So I came from, before I started to work with this, I worked with standard continued fraction and their dynamics. And usually when you work with 2x2 matrices, you always try to decompose your matrix into elementary matrices. And in this case, it is very easy to show that you get a diagonal matrix and then a row switching matrix and then two unipotent matrices. Right? This is the standard decomposition for continued fractions. But the interesting part is that even if you go to the y direction, which looks a little bit weird, you can actually get a similar decomposition. Right? You get a unipotent, diagonal, row switching, and another unipotent. So you get a decomposition for elementary matrices more or less the same and almost in the same order. Right? If you can look at it, so diagonal, diagonal, row switching, unipotent, and unipotent. So they are the same up to some cyclic permutation. And also you need to remember that in the end, we're going to multiply many of these matrices one after the other. So this cyclic permutation does not change too much when you have a lot of them multiplied together. So in a sense, once you have this matrix field, the conservative matrix field, all the horizontal directions are actually continued fractions, polynomial continued fractions. All the vertical directions are not polynomial continued fractions, but there is a hidden polynomial continued fraction there. Okay, so this is really nice and interesting property for this new object. And let me give you some more. So again, we have this conservative matrix field, which is in a sense is a lattice inside R2 of vectors of rational approximations. And when we want to understand it, we first start with the first line. And as I said before, usually we think about this construction as starting with the first line and then constructing the matrix field above it. And in many cases, under this construction, we fully understand the first line. And then the next natural question is what happens in the other horizontal lines? So each one of them gives us rational approximations. And as we saw before, under these constructions, all of them are polynomial continued fractions. So for example, you can use the recursion on the Pn and the Qn. So now that we more or less understand the horizontal direction, you can ask what happens in the vertical direction. So for example, let's take the third arrow. So you multiply two matrices in order to get there. And now you change the parameter of the matrix in order to go up. So the two matrices are polynomial, so the product is a polynomial matrix. And you now just change the parameter of this matrix. So in a sense, so what we get is that P and M, if you change the M, is going to be polynomial in M. So going horizontally, you have the recursion, and going vertically, you get a polynomial function. Okay, so this is the vertical direction, but also we just saw before that the vertical directions, in a sense, hide in themselves an extra polynomial continued fraction. So once you look what exactly happens there, in a sense, you get a dual conservative matrix field, which is some sort of reflection to the x equals y axis. So we have also this PM hat and QM hat. Okay, so these are four nice properties. And finally, we have the conservative condition, which I don't have too much time, so I will try to finish faster. And if you try to ask what does the conservative matrix field gives you, then it gives you this nice reciprocal condition. And this is really important because, for example, if you want to understand what happens when you go in the horizontal direction, so you look at the Q and M, where M is fixed and you go with N to infinity, then it means that you need to understand what happens at q and 1. But again, this is the first line, so we understand it quite well. And for example, in the zeta 3, we saw that it is n factorial cube. And we need to understand the other side, which we just saw that m is fixed and only n goes to infinity. So this is now a polynomial divided by a constant. So we have this nice decomposition where you want to understand this part, and this is a nice factorial times a polynomial divided by a constant. And in particular, in the zeta 3 case, the qn1 is actually divides the qn n plus 1. So all of these terms are integers, which is very interesting because then you can say that this qn n plus 1 is an integer times this n factorial cube. And remember that the first improvement that we had used the fact that we have very large GCD. So if your number is n factorial cube times some integer, it is very easy to find divisors. Okay, so these are all interesting properties. And again, I want to emphasize that what I find so interesting about this construction with respect to Apéry's proof is that once you have this matrix field, all of these questions are really natural, right? You ask what happens when you go on the bottom line, what happens when you go at the horizontal or vertical lines, what is the conservative condition give you about these polynomials? So all of these are really natural questions to ask, maybe not as easy to answer, but it is natural to ask, and this led us eventually to the result. Okay, so just to say how do you prove at the end what happens, then you start with the first line, and again, you need to think that this converges to zeta 3. You go to the second line and you think that it converges faster to zeta 3, then you go to the third, and then you go to the fourth, and then you do this diagonal argument and go along the diagonal in the conservative matrix field, and this eventually will converge fast enough in order to show that zeta of 3 is irrational. And again, you use all these properties along the way. Okay, so I will not go more into this, the proofs of this. This is the ideas, and this is the intuitions that we have about the conservative matrix field. And I will just say a little bit where we can go next after knowing that we have this matrix field and this construction. So first, the proof that we have so far only works for the matrix field of zeta 3. It's not such a big problem. The only reason that it works for zeta 3 is because zeta 3 is a simpler matrix field. In its sense, it is dual to itself. So all the computations are really easy. I think it can be extended to other matrix fields. We just need to find the right formulation. So this is not such a big problem. The other problem, which I think is more interesting, is that so far, all of the matrix field under the constructions that I told you, the F and F bar are of degree at most 3. There are of degree larger than that, but they are, in a sense, degenerate. And we're not sure if this is because we didn't look for hard enough, or we didn't look in the right direction, or there is some of intrinsic reason. I believe that there is an intrinsic reason. Let me give you my intuition why. So if you look at the matrix field of zeta 3 and you look on F and F bar, the roots of these polynomials are roots of unity of order 6, which are algebraic of degree 2. So if you work over 2 by 2 matrices and you tell me, okay, there is some limit to the roots that you get there, which are algebraic of degree 2, this sounds reasonable. And it also sounds reasonable that you can find something of higher degree. So this suggests a few directions of how you can extend this sort of theory. The first is what we talked before. We worked so far over Z, but we can try to work over Z of I or Z of square root of 2 or any integer ring extension. Another approach is just don't work over 2 by 2 matrices, work over 3 by 3 matrices, work over 5 by 5 matrices. And for me, at least, is the idea of working over high dimensional lattices. So these are two approaches. Another one, which I think can be interesting, is that we looked at the error rate and we wanted the error rate to go to 0 as fast as possible. But we also wanted that the GCD will go to infinity as fast as possible. And this determined how we can improve the original approximation. Now, going to infinity is more or less saying that the p-adic norm goes to 0. So in a sense, you get the infinite norm goes to 0 and the p-adic norm goes to 0. And maybe there is some sort of combination, which is really nice. So this is something that happens in many number theory problems, and I think that it should happen here as well. So these are three approaches. These are mathematical approaches. Another one is, of course, don't work with the constructions that we found so far. Maybe there are other matrix fields. Actually, we have other matrix fields. We just don't have, they're in a sort sporadic, so we don't have a nice construction for many of them. And maybe there are all sorts of interesting results. And of course, there is another approach which saying, maybe try to approach it algorithmically. And here I will reference we have a website where we have a lot of results there, and say, maybe I can use algorithms to find many more matrix fields and then find from there some sort of conjecture and say, okay, I have a new construction. I have a new matrix field, maybe in dimension 3, maybe in dimension 4. So this is another approach. And let me just plug in a couple of papers that are more about the algorithm side of this project. Of course, I talked about the mathematics side because this is more my expertise, but we have all sorts of results in the algorithm side. Okay, I think that this is enough for today. Thank you for listening. And if you have any questions, I will be happy to answer.
Thank you very much. Questions for our speaker?
Are you getting any kind of bound on the irrationality measure for zeta of 3 out of this?
Yeah, there is the delta bound. I'm not sure if you're familiar with it. I just erased it before I go back to the beginning. Right, we had this irrationality test at the beginning that I talked about, and we just wanted it to go to 0. But actually, we should think about it as 1 over q to some power. And you want this power to be as large as possible. Right? If I can write. This should think about it as 1 over q to some power. So if delta is positive, then it is irrational. And if delta is 0 is the trivial approximation. So using this approach, you can actually get this delta is positive. I don't remember exactly what is this delta, but you get the actual approximation. So yeah, I can actually compute this delta, but in many other of the other cases, we can compute it numerically. We still don't have a proof for exactly what is delta, but for the zeta 3 case, we understand more or less fully the matrix field, and you can actually find this delta.
But you don't recall what the delta is, or roughly? Are we talking about?
No, but I can check and tell you later. Yeah, I don't remember, but it is the same delta as in Aperi because we get exactly the same approximation as he does. Like we didn't improve the delta.
Other questions for our speaker?
Just checking, although I'm pretty sure I've heard the answer to this. It might have been some update that I missed. Is there any constant which was open before that you've managed to prove is irrational? I mean, a well-known constant.
No. At the beginning, what the people at the group, again, this was before I managed to do, is they managed to take the Catalan constant and improve the delta, which they didn't show that it is irrational, but they improved the delta that they could get. And so far, we don't have any new proof for irrationality. To tell you the truth, I'm more interested in the decomposition of the matrix field to these nice elementary matrices because it is much similar to the other type of problems that I know from number theory, but in the irrationality part, no, we don't have any new proof of irrationality.
So far, yeah.
Yeah.
Another thing I was wondering about earlier when I heard these talks, the books on continued fractions, which deal with the general case, will often prove things for functions. You'll extend, I mean, you showed an example yourself with a tangent. You prove an identity involving functions, and then you can apply it to various special constants.
Yeah.
So have you found any new function identities, any new expansions of familiar functions into continued fractions?
No. So in a sense, this is really elementary, right? We used Euler conversion. Euler conversion starts with an infinite sum and converts it to a polynomial continued fraction. More or less, the first thing of this work is to take the other direction and move from polynomial continued fraction to an infinite sum. And just from that, we build most of this theory. And there are many other, as you mentioned, working, for example, with functions, which unfortunately I don't know enough to tell you something about it, but I think that there are some nice approaches there that maybe we can combine with this work. But right now we don't know.
Other questions? If not, we thank Ofir again for a fascinating talk. And
Okay, thank you for listening and for the invitation.
yes, thank you.
Thank you.
Thank
So
you.
can you close your, perfect. Okay, very good. So I think this is our last seminar for the semester, because the last day of class at CUNY is Monday or Tuesday of next week, and I'm getting lazy. So thank you all. We'll start up again probably sometime in January. But
So-
if you do prove something truly exciting, let me know and we will have a seminar.
We lose.
Okay.
uh,
Before,
Yeah.
before we sign out, David Ross, you're at Hawaii?
Yes.
You have people there doing lattice theory, right?
Well, they're pretty much all retired now.
Ah, all right.
They're around. I mean, some of them are around sometimes, but yeah,
Okay.
no, we used to have a very, very strong lattice theory group, and we didn't
Yeah,
replace.
I mean, there's still things appearing on archives suggesting that a nation, I think, is,
Yeah.
active. Or,
Yeah,
so,
yeah, he's still around.
all right.
You have a question, or you plan
Yes,
to
a
visit
very,
here? And you,
a very specific question.
Uh-huh.
I want to understand roughly how many lattices with n elements are generated by 3 elements.
yeah, let me write this down. How many lattices with? I'm sorry, you said with infinitely many elements
With n elements, a
N elements.
combinatorial question, yes.
are generated by 3 elements.
Yep.
Okay. Well, if I see JB, I will ask. If I see any of them, I will ask. But the only one I usually see is JB. We had our departmental end of semester party already, and so that's usually the place where the retired faculty show up.
I emailed people, but I suspect that my emails will end up in the spam folders.
I don't know. Why would that be? Are you using an academic address, or are you?
No, certainly not.
Okay. Okay. Well, I will transmit, or if you prefer, you can send the question to me, and I can forward it to
Okay.
JB and Ralph. Sure.
All right.
Yeah.
My thanks.
Now you've got to keep checking your spam folder, David.
Yeah, no, I do anyway. Among other things, I'm editor-in-chief of a journal, and a lot of stuff ends up getting shuffled to spam, which I feel morally like I have to kind of look for, and so I do a daily filter of the spam folder. 2 spam folders actually, because I have an official journal address and my regular address. Yeah, no, not not my favorite place to spend any time. There's a lot of really unsavory stuff that ends up in one's spam folder.
You're still getting Nigerian princes?
Oh yeah, all kinds of stuff. Yeah. Yeah, no, we used to have the lattice theory group here was really fantastic, and we used to get many really interesting visitors passing through just because of the strength of the group. But you know, we suffered from the usual thing where the people making decisions for who to hire were not necessarily interested in maintaining the strength of the department, but more interested in seeing if there were new bandwagons to jump on. And when I say people, I don't mean my colleagues in the department, I mean deans and provosts. You know, they hear through the grapevine that something is a really good, really attracts lots of grants, and that may be 5-year-old or 10-year-old information. But then they turn around and start pressuring us to jump on that bandwagon. I'm a little bit. Well, we almost lost number theory, but we actually that got kind of reborn. We actually have reasonable. Well, we lost one of them again. Reasonable number theory plus, if you include algebraic geometry in the group. It's the curse of a relatively small department, is that you lose a couple of people and it's a major impact on your offerings.
What is the size of your department?
Well, we're down to 26 or 27 regular faculty, and we have a few postdoctoral lines. When I came, we were at 39.
Oh, wow, that's a big drop.
Yeah.
Did enrollment drop, or did you just hire more graduates?
No. If anything, enrollment is larger, and we haven't hired more. Well, we have more graduate students than we did, yeah, because the state legislature used to not believe in teaching assistants. They thought you bring graduate students in from the outside, you pay them, and they leave again. And so somehow that's people taking advantage of the state, rather than the other way around, the state taking advantage of talented people from the outside to get them to improve the university for some number of years. But we have more now, though it's still a relatively small graduate program. No, we basically just teach. We teach larger classes. We teach more efficiently.
More efficiently? What in the world does that mean?
It means, for example, that our course scheduling is much more constrained. It used to be anybody wanted to teach a senior level or graduate level course in a topic. If they could get a handful of students, they could go ahead and do it. And that's not the case anymore. So, I mean, I think these are probably pressures felt everywhere, but at least everywhere, but you know, elite institutions. But we used to have it pretty good, actually. So I used to teach classes every semester. I'd have a class with 4 or 5 students. And our calculus classes, our big classes, were already also sort of under 25, usually 20 and 25, sometimes lower. So we don't have that anymore, which is sort of sad. But yeah, no, we had so what happened historically was Paul Helmos was in chair for a year, and the way that happened was the university